This morning's session is on astrophysics. Before introducing the speakers and saying a little about Freeman's contributions to astrophysics, I wanted to begin with a personal story. I first met Freeman when I was a graduate student. I'd been spending the last several months of my thesis trying hard to prove a result that I knew to be numerically correct but couldn't prove analytically. But we eventually decided, even though I couldn't prove it, we would go ahead with the final thesis defense. And my supervisor suggested asking Freeman to be on the committee. He very graciously agreed. I gave him the thesis. He read the thesis. The exam went fine. I got my PhD, and after the exam, Freeman quietly came up to me, of course, with a few pages of paper, and said, "Here's the proof." So I'm grateful not only for the proof, but for the fact that I passed. And we never wrote it up. I've always regretted that I didn't write a paper with Freeman on this, not because the result was particularly important, but it would have dramatically reduced my Erdős number. Freeman's contributions to astrophysics have been really quite remarkable in their scope. He's placed bounds on the time variation of the fine structure constant from a natural fission reactor that operated billions of years ago in Gabon. He carried out a beautiful analysis of the physics and biology in a universe that would expand forever, asking the question of whether there were strategies that would allow a civilization to continue life and communication and thought for the indefinite future. Sadly, this analysis is no longer relevant in the current cosmological model. He made influential contributions to the early theory of adaptive optics, the technology which is only now beginning to mature, that is beginning to enable telescopes on the ground to correct for the distortion of starlight from the atmosphere and enable them to surpass the performance of Hubble in angular resolution. I should say this is also a subject that our speaker yesterday, Will Happer, made extremely influential contributions to. Freeman's most important, I think, astrophysical contributions have been on the subject of life in the universe. This is a very difficult subject to work on, of course, because we only know about life on Earth, and so any of our theories and speculations are subject to extreme selection bias. Nevertheless, Freeman has regularly devised simple and elegant arguments that have dramatically expanded our understanding of the variety of forms that life might have and suggested novel strategies to search for it. The first of these ideas was a suggestion in 1960 that Malthusian pressures on advanced technological civilization might lead it to convert all of the mass in one or more of its planets into a structure that completely surrounded the host star and absorbed all of its radiation. The importance of Dyson spheres in particular is that the waste heat generates a detectable astronomical signature, a luminous infrared source with a temperature of about 300 Kelvin. But more importantly, that the properties of that source depend only on physics. It doesn't depend on the psychology of the civilization, and in fact, even if they wanted to hide the source, there's no way to do so. With current technology, we can search for Dyson spheres around 1 million or so of the nearest solar-type stars. So far, there are only a few candidates. None of them is compelling, but there's another factor of 10,000 stars left in the galaxy that we should still look at. Freeman has suggested that asteroids could be colonized by genetically engineered plants that grow their own greenhouses. He's suggested that giant impacts could eject water and life from the subsurface oceans that we believe to be present on Jupiter's satellite Europa, so that the best way to look for life on Europa is to send a Jupiter orbiter to look for freeze-dried fish. He's pointed out that the best place for human colonization in the solar system may be the Kuiper belt of icy bodies outside Neptune. This has the particular advantage that you can build countries by tethering the Kuiper belt objects together with wires, and if you want to secede, you just cut the wire. He's argued that exponential growth of populations implies that by far the most likely place to find life is in an environment where you have the maximum Lebensraum, where you can expand particularly beyond your own body at the minimum cost in fuel, and therefore that the most likely place to find life is not on planets, but rather on comets, where you can move from one comet to the other much more easily. He's famously said, "I'm willing to bet even money that when the first alien life is found, it will not be on a planet, but I'd be happy to lose the bet." Freeman is not just interested in astrophysics research. Last spring, the Institute hosted the 50th anniversary celebration of the Amateur Astronomers Association of Princeton. Among the events was an award to Freeman as one of its most active, longtime supporters and members. I commented on the time to the president of the association that Freeman always seemed to turn up in unlikely places, and she said yes, that had been her experience as well. A few months before, she'd gone into a diner on Route 1, and there were a couple of tables filled with what looked like a motorcycle gang. This made her a little nervous until she realized that Freeman was in the middle of the motorcycle gang talking to them. Well, one of the most remarkable developments in astronomy in the last 2 decades has been the discovery of thousands of exoplanets, planets orbiting stars other than the sun. Given Freeman's interests, we didn't have to be rocket scientists to figure out that we should have a speaker on this subject, and our first choice was Sara Seager. Sara was an undergraduate at the University of Toronto and got her PhD in astronomy at Harvard, from where she moved here as a postdoctoral fellow and a long-term member. She's currently the class of 1941 professor in the Department of Earth, Atmospheric, and Planetary Sciences at MIT. She's received a long list of awards for her work. Just this week, she was part of the 2013 class of MacArthur Fellows. She's the author of the standard textbook on exoplanet atmospheres. She was a member of the group that made the first direct detection of infrared radiation from an exoplanet. And she currently splits her research time between theory of exoplanet atmospheres and novel concepts for space hardware for exoplanet research. Sara.
Well, good morning, everyone. It's great to be here, and you sound like a great audience. So this is my first real visit back here since I left over a decade ago when I was a member here. And out of all the memories that are flooding back, one of the best is just the interactions with the people working here. And among those that stand out is, of course, Freeman. Now, Freeman often, it seemed like a lot, he joined the astrophysics table for lunch. And just yesterday, I was talking to a former physics member who seemed a little envious of that. You seemed, in his view, you were at the astrophysics table more often than you were with the other postdoc tables. But Freeman often would ask us about our work, or he'd tell us what he was working on. And I always just loved his incisive, humorous, and sometimes sarcastic comments about things. And I just want to say it was just so great to have so much casual time with Freeman. So thanks, Freeman, and happy birthday.
Thank you.
And I'd also like to say that here I see some of the Institute trustees and friends of the Institute and board members, and it's good to see you too. And I think some of you will remember that I gave a talk to you about a decade ago. Now, I'm pretty sure you're not going to remember the details of the talk, but I hope that you'll get the point that a lot of the things I talked about then were here's what I'm working on, here's what we'll do in the future. But now I'm back, and I'm telling you all those things that I talked about. We're actually doing them all right now. And I hope that you can keep that in your mind as I go through my talk. So here's what I'm going to talk about. And just so we're all on the same page, because occasionally I do still meet a person who hasn't heard of an exoplanet, I'll just start in the simplest way possible and say that every star in our sky is a sun. And if our sun has planets, we would naturally expect that other stars to have planets also. And they do. We have nearly 1,000 what we call confirmed exoplanets, thousands of more planet candidates. And astronomers have found, statistically speaking, that every star in our Milky Way galaxy should have at least one planet. Now, after all that hard work, we have found that here's a schematic of our solar system. Our solar system is somewhat rare. Because we've found so many planets and been able to do some statistics, it seems that it must be less than 1 in 10 sun-like stars, or maybe 1 in 20 sun-like stars, could have a planetary system like our own. Now, our own solar system is quite hard to find compared to what we have found so far, so we still have to wait to really be certain about that. But what we have found is just a truly astonishing diversity of exoplanets. They've been found at nearly all sizes, all masses, all planet-star separations, planets having years or periods less than a day, planets that may be so far from the star we're not even sure they're bound to their star. And I just wanted to tell you about a list of a few really exotic planets. One of my favorites are these so-called super-Earths, rocky worlds that are bigger than Earth or more massive, that are so close to the star that they're heated from the outside, and we think that their surfaces must be so hot that they have liquid lava oceans, not from volcanoes, but just because they're heated so much from the outside. Another favorite planet is there's a lot of really low-density planets out there. And we're thinking, at least hoping, that some of them are so-called water worlds. This is still a theoretical idea, but we hope to prove it someday, where they would be planets that are 50% or more mass, water by mass, like Jupiter's icy moons, but a scaled-up version. And those ones are interesting because the hotter ones, they could be water having thick steam atmospheres, and as you think about traveling down into the surface and the interior of the planet, they wouldn't have liquid water, they're too hot, but they would have a layer of superfluid water. And then even below that, some kind of high temperature water plasma. And so that's actually a planet that we're excited about. Other interesting things to mention are planets that orbit 2 stars, circumbinary planets. And it's interesting to think about life and habitability and what it would look like in the sky on those planets. Also, astronomers have found compact multiple systems. That is, think about 5 planets in a system, in a plane, all orbiting interior to what would be Mercury's orbit in our planetary system. And they're not all rocky planets either. Some of those are those low-density planets I mentioned. Now you can see this list could go on like literally forever. And it's just so astonishing. I just wanted to convey to you at the beginning how diverse these planets are. And many of those examples I gave you are from the Kepler Space Telescope, no longer functioning, but it has just a legacy for exoplanets. So just to finish this introductory part of my talk, I want to tell you about my favorite example in exoplanets from the last decade, and one that, when I was giving my talk to you 10 years ago, I never would have been able to imagine. And that is the question of what is the most common type of planet out there. I used to personally think it would be like a Jupiter-size or Jupiter-mass planet. And we used to use a sort of analogy of like Microsoft. Like you have a company that grows so big and kind of sucks up a lot of the things around it, so there can't be another really big company like it. And that's our analogy for Jupiter and Jupiter formation. It would start to form and just gravitationally capture all the material around it and not really leave room for something else. But in this figure here, it's a diagram, a bar chart showing you the fraction of stars with planets. They're somewhat short periods, less than 50 days, but there's evidence from other exoplanet data sets to show we think this also holds for longer periods. And you can see this bar chart here. At the bottom, it's planet size relative to Earth. And they said I had to use this because it's an LED screen. So look at this. These ones are low here. 11.3 times the size of Earth. This is about Jupiter. Jupiter-sized planets would be here on the chart. And look over here. Neptune would be about here. And these are the small planets, 2 Earth radii. So 2 Earth radii planets, it turns out, are something like a factor of 10 times more common than a Jupiter-sized planet. And what is so cool about this result is that we don't have any solar system counterparts of planets between 1.5 and 2 Earth radii. And these 2 to 3 Earth radii planets, we don't even really understand how they formed. They're too big to be pure rock, so they must have some kind of significant gas layer. But remember, they somehow their growth was halted. We're not really sure. We don't have a consensus on how they formed. So I wanted to leave that one thing with you that you could take away. Remember this part of my talk, and you could tell your friends and your family and your children, the most common planet in our galaxy is something small, and it may well be these planets. We don't know how they formed, and we have no solar system counterparts. So out of all the stars and all the planets out there, the ones that we're most interested in are the planets that could be habitable. That is, they could have life on them. And there's a big push in this direction now. And so the next part of my talk, I'm going to tell you a few things about the habitable zone. Now here, the way we like to think about this, it sounds somewhat conventional, and in the question period or after my talk, I could answer more details for you. But we are somewhat terracentric. All life on Earth requires liquid water. So we'd like to find a planet with surface liquid water. And rocky planets with thin atmospheres are heated from the outside. And so we're thinking they're heated from the star, and that dictates the surface temperature with the sort of greenhouse stuff that I'll come back to. And so we want to find planets that are a certain distance from the star. Not too hot, not too cold, but just right for water, just right for life, and we call that the habitable zone. So one of the questions I get asked most often are there any habitable planets we know of today? So there's a website you can go to, and it's current potentially habitable planets. You can see here there's like a dozen of them. They go into some kind of detail. And I'll just let you think about this for a second. But I know there's at least one person in the audience who's paying attention to what is hype and what is science. And so I just want to convey to you like a little email exchange that's kind of been ongoing in the community. And before I get to the main point, you know what's happening is that we have almost 1,000 exoplanets now. And this question just started yesterday, discussion among exoplanet people. It's a kind of big list of people. I don't know who's on the list, though. It's like, what should we do for the 1,000th planet? Should we celebrate? But, well, it sounds like you're thinking we should, but no, the problem is we don't have a good definition for a planet. And even if we did in terms of mass or size, the mass and size uncertainties are so big, we wouldn't even know which are planets. We couldn't all agree on which are actually planets. And then there's the problem of, well, sometimes they get retracted. There's a bunch of issues. But what in this email exchange, one of the people wrote, I just wanted to read you the email, so I just brought it here. And he said, I'll just try to paraphrase it for you. Wait, excuse me. Hello, I'm not a scientist, just a journalist. If I can propose you something very respectively, like he's from another country, so some of it's a little awkward, but if I can propose you something very respectfully, it would be please, please, please don't ask at each of your discovery of the 100,000th exoplanet, is this planet habitable? Is this planet situated in the habitable zone? Is it possible that around this non-habitable planet, there's a habitable satellite, et cetera, et cetera, et cetera? And so what he's getting at here is that if you read the news and you're paying attention, it seems like there's a habitable planet discovered like every week or every month. And that's what he's saying. So I wanted to share that little story with you because it's good. I'm glad the journalists are now realizing that they're not all habitable. We don't know. We don't have enough information. This is just artist conception. We don't have a picture of planets like this. We see them indirectly. We know something about their mass and their size. We don't know, we know how much radiation is falling on them, but we don't know any more details than that. We'd have to know something about their atmosphere and the greenhouse effect to know whether these planets have a surface that's really reasonable. So in that light, I'm just kind of joking here, okay, but I thought you might want to continue the tutorial from yesterday on radiative transfer and cross-sections and things like that. It was very detailed, you know. But what I did want to say in just the spirit of science is that we do acknowledge, I don't work on climate on Earth, so don't worry, I work on climates on exoplanets. We all acknowledge that, this is actually a slide from my class that I'm teaching this semester. You know, we have this equation, people have figured out how to solve it over many decades. This describes how radiation gets absorbed and re-emitted in the atmosphere. We have numerical techniques, we have computer programs, and it's really a lot of the input physics that we don't understand. So if you think you have a problem on Earth's atmosphere, we have a much bigger problem when we're thinking of exoplanets, because some of them are quite hot, and we don't have molecular line lists at these higher temperatures. The cross-section problem, it's even bigger for us. You think you have a problem understanding the collisional broadening coefficients? We don't know how to approach that at higher temperatures. Some of the molecules people won't study in the lab, like methane at 1,000 degrees. They don't want to have an explosion. So I didn't want to say anything too negative about my field, but I'm sort of trying to be realistic here. We work through these equations too, and we appreciate that our models are kind of a bit out there. I might come back to this in a minute, but I just sort of wanted to try to tie into yesterday. So what I did want to do is talk about the greenhouse effect and exoplanets. Because if you think it might be a problem here, or might not be in some cases, we have a much bigger problem for exoplanets. So I'm going to start with this diagram. You may have seen it, sort of a standard textbook diagram of the so-called habitable zone. And what you're seeing here is, oh, right, this doesn't work. All right, what you're seeing here is stars, massive star relative to the sun. So this would be our sun. On a scale, it would be 1. We have small stars, like half the mass of our sun, or half the size, rather, twice the size. And these are our solar system planets, radius of orbit relative to Earth, so here would Earth be. And here's the so-called habitable zone in this cartoon diagram. And what it's showing you is that low-mass stars have low luminosity. So that a planet that is habitable would be closer to the star because it's just getting less radiation from the star. All right, so this is our picture. And this picture is quite terracentric. Oh, like 1 million people are now working on this. It's sort of one of the popular topics in exoplanets. The way it's described is that on the one side, we have runaway greenhouse. That is, if a planet is too hot, the water vapor will fill the upper parts of the atmosphere. It will get photodissociated with hydrogen escaping to space, and you would just get a runaway effect and lose all the water, and the planet would, by our definition, not be habitable. On the outside, it's that condensation of carbon dioxide. So we heard a lot about carbon dioxide yesterday. Imagine if the planet is so cold that carbon dioxide is not in vapor, gas form anymore. It's frozen out like Mars has frozen carbon dioxide. Actually, that would be a problem, because then you wouldn't have a greenhouse gas, and your planet will not be habitable. And that's been conventional definition for a while, typically assuming a CO2, H2O atmosphere. But remember when I started my talk and I told you just how diverse exoplanets are? We actually don't know. We don't have an a priori way of understanding how massive an atmosphere will be. Is it going to be like Earth's? Is it going to be much more massive? Is it going to have other gases that are greenhouse? And so I actually, that's for Earth-like planets, I actually was asked to summarize this for this invited review article that came out in May in Science. And I wanted to just share that with you. Because in terms of the habitable zone, things are changing. And I think it helps, it kind of captures the theme in exoplanets of diversity, and that nature is more creative than we are in terms of what's out there. So this diagram, it looks like the other one, but the curves are actually real models now put on this diagram. The planets, those little marks are actually planets. And that blue, it's a little hard to see here, so you could look at the side screen so it's not fractionated. But what you see here in this blue area is the so-called traditional habitable zone I showed you before, the CO2, N2 atmospheres. And if you could look closely here, it's kind of hard to see. I mean, to me, this Earth looks like it's really close to the edge of our habitable zone. And that habitable zone was at 0.99 AU. So I think if you tie into that whole model and model uncertainty, I don't think we can trust the models to that, precision or accuracy. And in fact, we don't, it's like actually uncertain because of clouds are a big problem. We don't know how those are really controlling a generic exoplanet. But what I wanted to share with you was how planets could be habitable quite close to or quite far from the star. And in that sense, the yellow band is a concept that perhaps we have some really dry planets out there. Water vapor is our biggest greenhouse gas here on Earth. And if we can imagine a planet with a lot, less ocean, less water vapor in the atmosphere, it could actually be closer to the star and avoid the runaway greenhouse effect. But in that case, we don't want to have too little water vapor in the atmosphere, because then carbon dioxide won't rain out. And that's a sort of big picture view of that story of how planets could be habitable much closer to the star. Now, going further from the star is a more interesting case, and that is the thought that we could have planets that actually have hydrogen in their atmospheres, molecular hydrogen. They could be massive enough or cold enough to retain some of their hydrogen. And I just want you to know that hydrogen is a very potent greenhouse gas. We don't have it here, so we don't have to worry about it. And I'm going to just try to capture briefly why. There's two reasons. One is, if you remember back to yesterday, the last talk from yesterday, and remember the carbon dioxide and how it has these specific bands, rotational vibrational bands that are just absorbing small parts of the spectrum. Well, it turns out that hydrogen has continuous absorption if the pressure's high enough. And that's because hydrogen, it's a molecule with two atoms that are the same. It doesn't have a permanent dipole moment. It doesn't interact with radiation the same way a molecule like carbon dioxide does. But what it does have, it has a collision-induced dipole. And so if it gets a collision, it all of a sudden gets this absorptive power. And it's actually not in so much discrete bands, but continuous. And so it fills in like all the gaps of where radiation is not absorbed and becomes a very powerful greenhouse gas. The other thing is that unlike carbon dioxide, it doesn't freeze out at a relatively high temperature. And so planets if they have hydrogen, they'll keep that in gas form to very far from their stars. And that's what I'm showing here in this dark blue. There's a paper out by another group, and they show basically you could have a planet out to 2 AU or more. If it's massive enough and has hydrogen, it would still be habitable. And there's even a concept that planets could be habitable even free-floating, far from the star. If they have radioactive decay producing heat on the inside, and they have just the right greenhouse atmosphere with hydrogen, it could be the right conditions that it maintains that heat at the surface so the planet is still habitable. So I just wanted to convey to you that there's lots of things out there. We're trying to understand what is habitable and what planets to look for, because now the real search for habitable worlds is really ongoing. And in the next part of my talk, I'd like to summarize for you what's going on in the search for habitable worlds and how we want to find and identify them. So we have actually two ways to do this, because we need to look at the atmosphere and see what's in the atmosphere, see if the planet has water vapor that may be indicative of surface water oceans, see if we could maybe see gases that are completely out of equilibrium by orders of magnitude that we may be able to attribute to life. And these are we have two ways to do it. And I'll talk briefly about each way. One way is in this decade, so I want you to know that it's going on now. And if you invite me back 10 years from now, I actually may be able to tell you we have some kind of sign of biosignature gas. We're not going to be 100% sure about it, but we may have signs about it 10 years from now. And how that works is this whole field of transiting exoplanets. When a planet goes in front of its star, as seen from a telescope, you see the drop in brightness. You can see it now. This is for a Sun-Earth analog. You can look at, do you see the planet coming into view across the star? You'll see it in a second. Oh, hold on. I was going to say, unless we had bad luck and it goes right in the, where the crack is in the screen. Yeah. Yeah, for some reason it's not really showing up on here, so let me, I don't know why this isn't working. That's what I said before I started my talk to the people in the back. I said, one thing will go wrong, I just don't know which thing it will be. Okay, well, it's supposed to show you a little dot going across here. You can see this movie thinks it's actually playing, so I'm not sure why it's doing this, but let me just describe what would happen. You know, I'm just going to try one more thing. Yeah, it just doesn't want to play. Well, this movie isn't as important as my later one, so if necessary, I'll come back and show this to you. But basically, the planet goes in front of the star. We don't see any stars spatially resolved like this other than our sun, but we can see a tiny, tiny drop in brightness as the planet goes in front of the star, and that is a characteristic signal we call it a transit, and it's actually how a lot of exoplanet science is done today, including a lot of those examples I gave you early on. But what's so great about transiting planets is we don't have to see the planet on its own. We just see the planet and starlight together, blended together, but we can learn so much about the planet. And to just capture it in words here, you see the planet going in front of the star. We just see the star. But here you see the blue part around the planet is supposed to illustrate in an exaggerated way the planet atmosphere. And we can see light from the star that shines through the atmosphere. And we can actually pick up the planetary atmosphere signals by differencing when we see the star alone and when we see the star with the planet in front of it. So that's really cool. We've seen a lot of exoplanet atmospheres that way. We also have the case when the planet goes behind the star. In the combined light of the planet-star system, we can see it disappear and reappear. And in that way, we can get a handle on the temperature of the planet and maybe what's in the atmosphere. Now, I did have a great dinner conversation last night about how much of this is hype and how much is real. So I felt compelled to just put a few slides in to show you kind of current state of the art. I'm showing you the very best case here. So I hope you'll like it. I think it depends what field you work in. You may think it's terrible. But just remember that a few years ago, we had nothing like this. And that 10, 15, 20 years ago when I started in this field, no one ever thought the day would come that anyone could show a slide like this. And what this is, we call this a spectrum of an exoplanet. And along the bottom is wavelength. I don't know why they put it in angstroms, but here would be, let's see where we are here. So here's 10 to the 4 angstroms, or 1 micron. So this is visible wavelengths here, and this here is infrared. I can't have time to explain what this is, but it's just like an upside-down spectrum. It really is just the radius of the planet. It looks different if there's absorbing gases. But for our purposes, this gray line here is one model, and that's a cloud-free model. So these wiggles are like water vapor. This is alkali metals, Rayleigh scattering. But for your purposes right here, I just want you to see that this data, the black data points, some of these are from the Hubble Space Telescope, Spitzer Space Telescope. You can see, I hope you can, even no matter what, if you're a scientist or you're not a scientist, you can tell whether these agree or disagree with the model, right? And this is not to say the models are wrong. It's just they purposely are illustrating that we've learned something new here. This planet must have clouds and hazes that are blocking out these signatures of these molecules. Okay, so there's some kind of cloud or haze and some kind of other cloud here. Now, I want you to know that despite all the certainties and the fact that the models have uncertainties, they're not uncertain to the level that we don't understand what molecules should be there for a given temperature and pressure. And you can challenge me about this later if you want, but we're going to have water vapor in a hot planet, not because of surface liquid water, just because it's the dominant form that oxygen, it's hydrogen and oxygen together will make water vapor. The alkali metals, we expect those to be there also, and we've seen them in other planets. And I guess they would argue that this point here is related. Anyway, I wanted you to see we have real data. It's telling us real things. We have a handful of exoplanets where we have data like this. We have dozens more where we have worse data. And the field is really moving forward. We are really being able to begin to study exoplanet atmospheres. And just as a comment to how we handle this, because if you think we have a problem with Earth again, how do we study exoplanets? We kind of do, we can't really do the inverse model because you can't write the equations down and invert them. But we do a kind of approach, I used to call it the million model approach, but we just try to say, what can we say robustly about the planet atmosphere? Can we identify molecules? Can we say anything about how much of that molecule is present? And that's kind of the state of where the field is right now. Okay, so I guess I should probably just talk briefly about our current favorite exoplanet. There's always the favorite that's popular, and then later on people forget about it. But I think I just have to say this because I wanted to have a few things in here for my friends here who are working on exoplanets. And here's another case again where, not explaining it in detail, but just showing you there's this case with the red features, model with red, model with blue data points. I wanted you to see there's a lot of data, right? We call this a lot of data. And you can see that red model is completely ruled out. And what that red model is in this case is it's a, we're imagining this planet GJ1214b. We're hoping it's one of those water worlds, that's exotic water world. And we've ruled out the case that it has a no cloud-free atmosphere that's hydrogen dominated. Because again, some of you you don't have to get this part of my talk to understand the rest of it, but if we have a hydrogen atmosphere, it's more puffy. It's got a lower molecular weight than like a carbon dioxide atmosphere. And if it's more puffy, it has a larger scale height, the atmosphere is just bigger, and we would expect these bigger features in transmission. And we've ruled that case out. So the data can tell us something. People love in exoplanets, they go crazy over poor data. I can't tell you how long one of my students, and partly myself and others, well, I had already done this in the past, so I don't do it now, but we're saying, oh, is this something real? You know, this little feature here, is this showing you that there's some kind of water vapor that's a smaller feature? So people spend forever. And right now, this very planet, there's 2 papers being refereed in Nature about it had some kind of problem. Okay, well, that's 2 problems that I didn't anticipate, so let's start again. All right, so maybe the movie will work this time. You don't need to see that movie. Okay, so where are we here? All right, well, anyway, I just wanted you to know there's a real search going on. We're excited about this planet. Again, here's another plot. Look at all the colors. They're just showing you different studies going on. Everyone who has a big telescope around the globe is looking at this particular planet. There's points on the curve. There's atmospheres being studied, and that's what I wanted to capture for you. So how does this relate to finding signs of life on other planets? Because these are all big planets. They're too hot. They won't have life on them. I was just trying to capture that there's real work going on in exoplanet atmospheres, and we have a real plan for the very near, what we call the near future in this field. And that is, we plan to find, that is related to an MIT-led NASA mission. It's going to be launched in 2017. It's called TESS, Transiting Exoplanet Survey Satellite. Our PI is George Ricker. And here it's showing you a kind of schematic of it. It's got 4 cameras, each with a 23 by 23 degree field of view, 100 millimeter effective pupil diameter, and about a 17 megapixel camera on each one. They're all offset from each other because they want a very overall wide field of view to survey the entire sky for rocky planets transiting small stars. So TESS is going to look at 500,000 stars spread across the sky and try to find a pool of planets that are big Earths transiting small stars that we can look at their atmospheres with. Now, our current telescopes won't do the job, but we have a telescope that's going to launch in the future called the James Webb Space Telescope, and that will be able to follow up just a handful of rocky planet transiting small star atmospheres. So I just tried to convince you that we're studying atmospheres now. We're going to do this a second generation for the smaller planets with different set of telescopes, and we're excited about this. So now I'm going to get to my, this is pretty much my favorite topic right now, and that is the Earth twins. Because what I told you about transiting planet, it doesn't work for Earths. We can find Earth-sized planets that are transiting, but their atmosphere, think of an annulus atmosphere compared to the size of the whole star, is just too small. We can't go to that many decimal places in our work. So we would have to do something different. We'd have to, what we call, directly image the planet. We'd have to block out the starlight and search for planets directly. And I'm going to just try to capture that view in a few ways. With the analogy, the way I try to describe this is that an Earth, think of an Earth twin, just like Earth, that would be, let's say, 10 or tens of light years away. It's not fainter than the faintest galaxies ever observed by the Hubble Space Telescope. The problem is it's adjacent to a very, very, very bright star. And our sun and Earth, their contrast at visible wavelengths is 1 part in 10 billion. So we'd have to block out the starlight to 1 part in 10 billion to be able to see the Earth. So this is a work. So this is a problem. So I'm going to tell you. Well, I was just thinking of how to say it. That Freeman has thought just so broadly and so out there. So I just wanted to try to convey to you real work going on in this direction. And I'm going to tell you about my favorite concept for this, and a lot of this is work done at Princeton that's come out of Princeton University, in particular by Jeremy Kasdan's lab, and David Spergel came up with the Spergel pupil, and it eventually led to this. It was one of the things that eventually led to this concept. And that concept is to put a star-shade telescope system in space, where the star shade is a specially shaped occulting screen to diffract the starlight away from the telescope. So most of you are familiar with this. If you observe a point source, you'll get airy rings. And those airy rings, the first airy ring, for example, is 100,000 times brighter than the planet you're looking for if you're looking at a star with a circular aperture. But if you have a specially shaped version, so you can't just put a circle in space, a specially shaped one, it actually can diffract to your advantage, and it throws all the light to the edges of the image. And so in this system, this star shade would be about 30 meters in diameter, tip to tip, and it would have to fly tens of thousands of kilometers away from the telescope. And this is a hard problem. That's to actually fly tens of thousands of kilometers away to within meters precision. That's like asking a friend to hold up a dime at 5 miles away and be perfectly aligned with you. So this is not easy, right? It's not an easy problem. But I'm actually going to show you a movie next. And if this movie doesn't work, I actually have a way I can show it to you. Okay, so this movie, yeah, you know, this is funny because I tried these before and it really worked. So I'm going to have to do something a little different. So I may need like an extra couple minutes here. So hold on. Okay, I have to actually escape out of this now. And you're going to see my messy desktop. And I'm going to go to this. I have to actually go to the movie directly now, so I can just show it to you in another. So, okay, let's see. All right. Okay, so I'm just going to open this movie and show it to you separately. All right, so what I'm showing you here is an animation of the star shade and telescope being launched together, and the petals, those specialized petals, would unfurl from their stowed position, and a truss would expand with the petals snapping into place. And the precision that these have to be cut to is like tens of microns, and there are other tight tolerances. This star shade would then fly with its own propulsion far away from the telescope to the tens of thousands of kilometers and block out the starlight, and so that the hidden planets can be seen. And I just want you to know that this, actually, of all the ways to do this, there's many ways to solve the direct imaging problem. This is actually the most effective way to do it with a relatively small telescope. And if you think about it for a second, there's a number of reasons why that's the case. But one is that the spatial resolution problem with the telescope, you're throwing some of that problem to the occulter. It's doing the blocking out of the starlight for you. And another problem is that with this complicated, okay, well, I'll leave it at that for now, and you can ask me some more questions. So I'm glad that some of you laughed about this, because, you know, again, it's that theme in exoplanets: is it hype or is it real? And so I'm really, that's why I'm even more happy to show you the next video. And this one is actually showing you, again, work led by Jeremy Kasdan. And this is a demonstration that was just done a few weeks ago out at Northrop Grumman, where these petals here, this system is 2/3 scale, but it would still work. It's still the right optical design to do the job in space. And what you're going to see here is a time-lapse movie with a truss. And this truss is heritage. It's been used for radio deployments of large radio devices in space. Time-lapse movie showing you the truss expanding, and the second stage of the petal deployment. Now, there's so much technology work ongoing here, I couldn't summarize it all for you. And this may look a bit primitive as compared to the animation, but I just wanted you to know that we have a handle on the technological tall poles here. There's one more to go that hasn't been studied. But on the whole, there's many reasons why we think this is very viable. And right now, I'm actually chairing a mission study concept that was called for by NASA to do this one. So if you have any questions or you want to challenge issues or why we think this is doable, I want you to ask me about that later. Okay, so now I'm going to go back to my talk and get back to it. Okay, so then the question is, what are we going to do once we actually find the planet in the planet atmosphere? And what we really want to do is try to find biosignature gases. And I'll just say to you that this is the type of thing that if I was going to have lunch with Freeman again, this is the project I would tell you about. And it's not really ready to me to tell you, but I wanted to just capture how to try to think about the problem, because we're so terracentric. Here on Earth, oxygen is our favorite biosignature gas produced by life. We've considered other things that are not unique, like methane or nitrous oxide. We consider things like DMS, dimethyl sulfide, that's produced by plankton in the oceans. I could give you a very long list. But how do we know what to look for in another planet? Especially when we may only have a handful of planets to study in the next decade or even in the future. And so one thing I set out to do, I know I'm running out of time, so I can't tell it to you, but I wanted to start out with, this is supposed to be a funnel, start out with all small molecules. that are stable and volatile, and sort of sort through them all and say, well, which ones under some generic constraints could actually be biosignature gases. And eventually you'd get down, and I can't have time to go through all the criteria, but find out into categories which ones should we really look for. It turns out for exoplanets, you should just look for anything that's unusual and doesn't belong, and then kind of try to back it out. But the thing that I would tell you if I get to have lunch with you again is I discovered this kind of interesting thing, I thought, that when I started looking at all small molecules, because I wrote a chemical combinatorics code, and yeah, you get up to really large numbers tying into yesterday's talk. And then out of the ones that are stable and volatile, each structure, each molecular formula could have like 10 or 20 structures. So I got hundreds of thousands of molecules. How do you know if they're real or viable? That's sort of another story. I ended up learning Python and writing a code to scrape websites to see. That's not like proof or anything, but it's a sort of journey. And then I started finding out that all the small molecules, the small ones, were produced by life. It was amazing to me that pick something small like carbon dioxide, even ozone is produced inside some cells. And I just sort of stumbled across this whole thing. And I'll just tell you one funny story before I move on to the next part of my talk. But that was, you know how I bet a lot of the astrophysicists here, I'm sure people write to you with their crank theories, right? Like, here's a theory of physics. Well, I was like a person with a crank theory in biology. And I had two biochemist friends. We've worked pretty hard on this project. And we went to talk to a Nobel laureate in physiology and medicine, Jack Shostak. He's an astrobiology person. So I went to him with my theory, and he said I was approaching it wrong, and it wasn't right, and it had this problem and that problem. But actually, it's led to a whole other thing that I think is really going to flourish, of understanding the sort of parameter, space that biochemistry is moving through. And so I can tell you more about that later if you're interested. But, right, I'm going to have to cut this part of my talk so I have enough time. I was going to tell you about my model atmospheres and other work I'm doing in biosignatures that's a little more conventional and mundane. But for my astrophysics colleagues, you can just look at some of my work on AstroPH last week and read about it there. I did want to wrap this part of my talk up by talking about, just very briefly, about Dyson spheres. One of the times that we were having lunch with Freeman was the day that he was awarded the Templeton Prize. And so we got his first-hand reaction to that one. And I wanted to tell you, Freeman, in case you didn't know, but the Templeton Foundation now is sponsoring a study to search for Dyson spheres. And it's my good friend and colleague, Jeff Marcy, who's doing this. And he's doing it with Kepler data. So the concept is that there is a Dyson sphere. I couldn't show you the movie, but the transiting planets, if there is a Dyson sphere, the point is that we will see that the star brightness varies non-astrophysically. This is Jeff's slide, and these are his words. And I don't have time to go through some of his examples. He doesn't have any real examples, but the point is there's this exquisite data set of hundreds of thousands of stars, and it's a different concept from the one that Scott described of looking for infrared excess infrared, but it's really going on now. So I'd say that partly with a smile, but why not look for it? I mean, there are actually such great data sets out there. So for the last part of my talk, I'm going to skip this. I wanted to just address something to you about what I call the small satellite revolution. And before I start, how much time do I have left here? 5 minutes. Okay, that's enough time. Because this field of exoplanets has been just completely crazy. When I first showed up here as a member in 1999, like literally most people in the world thought it was a field that would absolutely never happen. My mentor then, John Bacall, he believed in it. And I just wanted to, he believed in the concept that if you had a great idea and you could back it up with physics and it was doable sometime in your lifetime, then you should absolutely pursue it. And that to me like embodies the spirit of the Institute and the people that work here. And that's the one thing that I carry with me pretty much every single day. So I wanted to relate to you this small satellite revolution, because besides exoplanets, I haven't seen it in any other field, and I'm starting to see it in this field, and I wanted to just share it with you briefly, because I think it's ultimately is what's going to end up opening up space for travel, at least travel interplanetary. And that is this field called CubeSats. And I was going to tell you about my own project, but I'll leave that out for now, just in the spirit of getting things together. But what CubeSats are for those of you that don't know about this field, you know the phrase 3 peas in a pod. I like the phrase for this one, 3 CubeSats in a pea pod. CubeSats are 10 by 10 by 10 centimeter satellites, and you can put 3 of them in a standardized deployer, and they're getting launched on, over a dozen or more different launch vehicles. They're launched on a pea pod that's shown here, bolted to the upper stage of a rocket. It's kind of hard to see here, but these are the 10 by 10 by centimeter units. And so what this has actually ended up doing was it gives you cheap, frequent access to space. It gives you standardized platforms. So now when you talk about heritage components, it's not just a component that has to be redesigned. It's actual hardware that has flown many times. You just buy it, kind of like glorified Lego. I'm pretty sure that most people in this audience, if you wanted to spend tens of thousands of dollars on the satellite and another 50,000 on your launch, you actually could build something and talk to it. You could just program it. You could learn how to do it, and it would be no problem. But what it's ending up doing is it releases the traditional barriers to space, including risk and cost. It's allowing all sorts of nations to participate in space that hadn't before. But the best thing is that it allows you to test new technology. So you can go up there cheaply and easily and stick some new technology in this system that you've just bought the rest of the components for. So people want to test stuff like proximity operations, new types of micropropulsion, novel communication systems. But the most important thing is how it's changing the mindset of the next generation of space engineers. So this thing is ongoing. The first generation of grad students have built these things now. And all of a sudden, a couple years ago, they wanted to have a conference about interplanetary CubeSats, sending one of these little things like on its own to Mars or the moon. And they were like, so they had this meeting at MIT, and they asked me to give a talk, and I was like, fine, but no one's going to show up. I'll just come and do it. And I get to this talk, and there's people from all over the world and people from high up in JPL, because no one told the students you couldn't send these things interplanetary, It was just like in exoplanets. No one told them they couldn't do it, so they just think they can do it. And indeed, the first couple of them are going to be, lots of these have launched, hundreds of CubeSats, but the first two that are going to leave, I think they're going to send them to like a geotransfer orbit, and they're going to have their own propulsion and just send them out there and see what happens. But it's not just that. Now the big space missions that are going to go to Mars or beyond, they're going to carry CubeSats with them. And in the future, we'll see people building their own things that can be dropped off on another planet. So that leads into, I only have just a few more slides. I'm trying to get this story together here, but this is showing you satellites launched over the last 30 years. The yellow one are the satellites that are less than 10 kilograms each. So you see, before it never happened, now it's the dominant thing that's being launched. And how is this going to lead us, and how is it related to exoplanets? Well, I just wanted to mention asteroid mining briefly. But what I didn't have time to talk about was my satellite that I did a CubeSat project. It's still ongoing now. And it's a tiny space telescope that we plan to send first one, then a dozen, then 100 of them to low Earth orbit, and each will look at its own very bright star for a transiting planet. Now, I'm not going to have time to get in the details of why we're doing that, but I just want you to know that the asteroid mining folks picked up on the technology we had, and Peter Diamandis called me. He actually came to see me in person and asked me if I could join forces with their planetary resources mining company, just for a specific technological reason, that we have to be able to point this small thing very precisely, and there's many disturbances in space. But one thing these asteroid miners are going to have to do is when they have to have their own communication network. They can't use the deep space network. And they want to do laser communication from far away. And they also need precise pointing because they have to acquire, let's say they're 1 AU away and they're looking back. They have to be able to acquire their communication satellite in low Earth orbit. So they asked me to help out there, and I got to also join their board of advisors. But in case you haven't heard of asteroid mining, the big picture is that the sheer amount of useful material, water, iron, nickel, sulfur, platinum group metals, et cetera, in an asteroid is compelling enough to motivate mining. And one of the most interesting valuations is that one 500-meter diameter asteroid, platinum-rich asteroid, actually has as much platinum in it as has been mined in the history of mining. So that's a kind of interesting thing. But how likely is it that this will happen? Well, this has been done by Japan here, and NASA's doing this. We're planning to go to an asteroid. It's a mission called OSIRIS-REx. Get to an asteroid, orbit it, go very close to it, scoop up 2 grams of material and bring it back to Earth. So we actually know how to do those things. We don't know how to mine in microgravity. We don't know how to reduce the cost, because after all, the NASA mission, that's $2 billion for 2 grams of material. But I was sort of just trying to I wanted to convey to Freeman in particular, I'm sure you've read all about this, but this sort of CubeSat thing of this new mindset, the asteroid miners, I've been to the Planetary Resource Lab. They have a really nice setup. The people that believe it can happen, sort of the narrowing down of we're going to do optical communication, we're figuring out how to mine in microgravity, we're able to bring stuff back. All this is really happening, and I can just see enough going on there that I really personally believe this will be a reality. So I wanted to finish just by saying, well, how is this related to exoplanets? Well, the first thing is to do that fancy terrestrial planet finder that I showed you the movie of, we need the costs to get to space to be reduced. And this is already happening as being motivated by the commercial space companies. Like in my study that we're doing, we're only considering, well, I can't say only, but our fiducial thing we're only considering the SpaceX Falcon 9 because it's like $100 million cheaper than the next launch vehicle that can carry a little more. So reducing the cost of space is critical, and it's only going to happen for other reasons that are motivated by other things than curiosity. The second thing is that for exoplanets, we really believe that we want to have this map of the stars and of other worlds out there. And with this map, what are we going to do with it? Well, we really hope that in the very far future, people are going to send probes to these other planets. But again, we can't do that unless we know how to do very complicated things in space. And we think that asteroid mining will actually enable this for us. And that's why I support asteroid mining. So to summarize my talk, I wanted you to walk away with the point that planet formation is truly a random process. And there's so many surprising planets out there, including these so-called mini Neptune-sized planets, which are 10 times more common than Jupiter-sized planets. And I wanted you to know if you could only remember one thing, take that one home with you. I talked about habitable planets and how, because of greenhouse gases and the fact that we don't know what atmospheres are made of, many more types of planets could be habitable than we expect. And to talk about how to find and identify habitable worlds, I tried to convey to you that we're studying atmospheres of exoplanets now, although the data is somewhat crude. But we have a plan to do our second generation with new space telescopes to look at small planets that are rocky, that are transiting in the habitable zones of their host stars. And we also are planning to work on direct imaging from space. And that work is also ongoing. So my closing thought is that I believe that in our lifetime, we'll be able to take I believe that where we're headed here is that in the future sometime, we'll be able to take our children or grandchildren or great-grandchildren or even great-great-grandchildren to space, to a dark sky, and to point to a star and say that star has a planet like Earth. Thank you.